Welcome to Propeller Breeze, the show for student pilots, sim fans, and everyone chasing that first solo and beyond. All information in this podcast is for entertainment and general knowledge only. Always verify with certified flight instructors or regulatory authorities before attempting anything mentioned here.
Welcome back to the deep dive. So, if you're a student pilot, maybe you're prepping for your instrument rating, or you're just someone who looks at a cockpit panel and wonders,
how does that thing work?
Exactly. How does that little thing know where the horizon is? Well, this deep dive is for you. We're tearing apart the foundational mechanics of instrument flight, the gyroscope.
That's exactly right. For instrument flight, you're taught the scan, looking at the gauges. But the real insight, the deeper understanding, it comes from knowing why these things work and maybe more importantly, how they fail.
Right.
Our sources today are all focused on those underlying principles, the design and the power systems that keep these spinning wheels turning.
So our mission today is pretty simple. We want to stop treating things like the attitude indicator, the AI, or the heading indicator.
The HI, the turn coordinator.
There's these magic boxes. We're going to get into the science so your instrument scan starts to feel, intuitive.
Okay, let's unpack this. So when we talk about a gyroscope in an airplane, we're not just talking about any spinning top.
Right.
We mean a highly engineered rotor that has to have very specific characteristics. I mean, what makes it reliable enough to literally bet your life on it when you're in the clouds?
It really just comes down to kinetic energy and minimizing resistance. So to start, the rotor needs to have great weight for its size.
High density.
High density. And why is that? It's all about inertia. The heavier that wheel is, the more it wants to resist any force trying to move it.
And you compound that inertia by spinning it at just incredible speeds. We're talking tens of thousands of RPM.
Wow.
All on bearings that are designed for the absolute lowest friction possible. The faster and heavier it spins, the stronger those gyroscopic properties become.
And once you have that perfect rotor, well, how you mount it completely changes its function. We're really just dealing with two main types of mounts, and it all depends on which gyro property you want to use.
Right. First, you've got the freely or universally mounted gyro. This is the one you'll find in your attitude indicator and your heading indicator.
Okay.
It's perfectly balanced and has 3 planes of freedom. What that means is, as the airplane, the instrument base pitches and rolls around it, the spinning rotor inside stays absolutely fixed in space.
And then you have the other type, the restricted or semi-rigidly mounted gyro.
Right. That's what you find in the turn coordinator.
And here, one of those planes of freedom is, well, it's locked down on purpose. That restriction is what lets the gyro actually sense and measure a turn. Not just if you're turning, but the rate of that turn.
Which brings us right to the science. What's fascinating here is that the function of every single one of these instruments, it all boils down to just 2 laws of physics.
Just 2.
Just 2. Rigidity in space and precession.
Okay, let's start with stability. Rigidity in space, that's the idea that the spinning object resists any change to its plane of rotation.
It wants to stay put.
It just wants to stay put, forever fixed relative to the outside world, no matter what the airplane does around it.
Yeah, the classic example you always see in the sources is the bicycle wheel.
Right.
When you're standing still, the bike is totally unstable. But once you start pedaling and get some speed, those wheels gain this incredible rigidity. The bike becomes super stable.
And the faster you go, the harder it is to knock it over, to change that plane of rotation.
Exactly. And that's the principle behind the attitude indicator. The rotor spins incredibly fast inside a set of gimbal rings.
And those gimbals are the key. They let the airframe, the base, just tumble all around it. But the gyro itself
Stays put.
It stays perfectly aligned with its original plane of spin, which to you, the pilot, represents the true horizon. That's your attitude indication.
So if rigidity is about stability, then precession is about movement. And this is where things get a little weird.
Here's where it gets really interesting. Precession is the tilting or turning of a gyro because of a force you apply to it. But this is the critical part.
Yeah, this is the part that bends your brain a little.
If you push on one specific point on that spinning rotor, the reaction doesn't happen where you pushed.
Nope.
It happens 90 degrees later in the direction of rotation.
That 90-degree principle is everything. It's the whole reason a turn coordinator can take the yawing of the aircraft and turn it into a visual signal you can read. The aircraft pushes on it, and that 90-degree reaction is what moves the needle.
And the rate that it reacts is so important. The rate of precession is inversely proportional to the rotor speed.
What does that mean in practice?
Well, if the rotor spins slowly, The precession is huge, it's rapid, it's inaccurate,
Useless.
useless. But if it's spinning fast, the reaction is predictable, it's stable, and it's accurate. This is our first clue about why continuous, stable power is so non-negotiable.
Let's go back to the bicycle to visualize that 90-degree lag.
Okay.
If you're riding fast and you want to turn left, you don't really steer the handlebars first. You lean.
You lean left.
Right. And when you lean left, you're applying a force to the top of the wheel, pushing it to the left. But because the wheel is spinning forward, that force doesn't just push the wheel over. The reaction happens 90 degrees ahead in the direction of spin, which is the very front of the tire.
Pushing the front of the tire left.
Causing the bike to steer left and execute the turn. It's precession in action.
That predictability is what makes the instruments work. But it also, well, it points to a major weakness, doesn't it?
It absolutely does. Even in a freely mounted gyro, like in the heading indicator, any tiny little imperfection, a bit of friction in the bearings, a slight imbalance,
Anything.
it applies a small, constant, deflective force, and that tiny force is still subject to precession. It causes the gyro to slowly wander or drift over time.
And that's the wander we're always told about. That's
Yeah.
why, as pilots, we have to manually check the heading indicator against the magnetic compass every, 15 minutes or so?
Exactly. You're just compensating for those small but inevitable precession errors.
But, all this marvelous physics just goes right out the window if we don't have enough juice to make it spin right.
That's the million-dollar question. What is actually spinning these things?
Because that spin speed is the master variable. It decides if rigidity works and if precession is predictable. So power redundancy is everything.
Right. Most aircraft will use both pneumatic, so vacuum or pressure, and electrical power.
So you have a backup.
You have a backup. Usually the AI and HI are vacuum-driven, and the turn coordinator is often electric. That way, if one system dies, you still have some source of bank information.
Let's focus on that vacuum system because it's powering the big ones, the primary attitude instruments.
Okay, so the system works by literally pulling air across tiny veins or buckets cut into the gyro rotor.
Like a little turbine.
Exactly, like a tiny turbine or a water wheel. This air suction is what spins the rotor at those crazy high speeds.
And the suction it needs, it's measured in inches of mercury, or Hg. And it's usually kept between 4.5 and 5.5 Hg.
That pressure range is the sweet spot. It's everything.
So how does the system maintain that?
Well, the sources lay it out pretty clearly. You have an engine-driven pump that creates the suction. Air gets pulled through a filter
To keep the gunk out.
to keep the gunk out. Then it's routed to the AI and HI to spin the gyros. There's a relief valve to make sure the suction doesn't get too high. And most importantly, there's a suction gauge right there on your panel.
And this, right here, is the big takeaway for any student pilot. That suction gauge isn't just some secondary system light.
No?
If we connect this to the bigger picture, it is the primary health indicator for your AI and your HI.
100%. The system rarely just fails instantly. It's usually a slow death. A pump gets worn, a hose gets a small leak, a filter gets clogged.
So the pressure slowly drops.
It just slowly drops. It goes from a healthy 5.0 down to, say, 4.0 or 3.5 Hg.
And what happens when that pressure drops?
The spin speed of the gyro decreases. And if the spin speed decreases, the rotor loses its rigidity in space. It's not rigid anymore. So instead of staying fixed on the horizon, it starts to wobble, to flop around, to precess like crazy in response to even minor turbulence.
So the instrument doesn't just stop.
That's the critical danger. It doesn't just freeze, it starts lying to you.
Wow.
A low vacuum reading means that instrument is actively giving you unreliable, dangerous information about your attitude or heading. It goes from being your best friend in the clouds to your worst enemy.
Which is why checking that suction gauge has to be part of your normal scan, just as important as checking your altitude.
And it explains why some planes have a specific warning light for low vacuum pressure. The engineers knew that by the time you notice your AI is acting funny, you're already behind the airplane. The crisis has begun.
So what does this all mean? We've gone from the physics to the hardware to the failure modes. Your stability in the clouds, that comes from the rotor's rigidity in space. Your ability to see a turn, that comes from the weird 90-degree delayed reaction of precession.
And all of it, every last bit, depends entirely on a properly working and constantly monitored vacuum system that keeps that rotor spinning as fast as possible.
So the ultimate takeaway for you, the pilot listening, is that the stability of those instruments is directly tied to the speed of the spin.
Which is directly tied to that suction pressure reading on your panel.
You just can't afford to skip that gauge in your scan. Ever.
And that leads us to our final provocative thought for you to think about. Given how absolutely critical continuous vacuum monitoring is for the stability of your AI and HI, and given that the main pump is driven by the engine, what assumption must you constantly question about your aircraft's power reliability, both electric and pneumatic, during every single phase of flight, especially when that engine isn't running at full cruise RPM? That little gauge is your only link to the physical health of your most important systems.
That's it for this episode. Keep your wings level, your brain sharp, and catch you next time in the pattern. Thanks for riding with Propeller Breeze.